I need both?
Yeah, I got both for sure. Okay. So one's for the recording, one's for the audience.
All right. Well, thank you for coming. Thank you for sharing this Saturday morning and afternoon with us today. I am a big fan of this place. I think the phenomenon of group houses and people trying to create the machine god in their living room is something we should all be happy about. I am staying in Berkeley for the next until late in February, and there we have another example of a communal living arrangement called Lighthaven, where they're trying to stop us from creating the machine god. So we are actually shooting a documentary. This man, John, in the back there is one of my partners. And we're trying to capture in that documentary that dichotomy between the energy, I would say positive energy in places like this, and then the concern that's being expressed by people in that other place. The tentative title for this film is Dreamers and Doomers. And we're going to be interviewing people from this community, people from that community, and I think we're going to do a fair job of letting everybody express their perspectives. If you are, for example, one of the authors of the 2027 AI Safety Risk Report, you think we're right at the cusp of things happening. So it would be, I think, our goal is to capture this moment in time in this most special place on the planet where all of this is coming to a head. And so today we are doing some shooting for the documentary. If you don't want to be in the B-roll, so a lot of what's shot today will just be some B-roll for the documentary. If for some reason you don't want to be in the B-roll, just let myself or John know, and we'll try to avoid shooting you. Like if there are federal charges you're trying to evade, or the Chinese government has been after you for a while, you don't want them to know that you're in the U.S. For whatever reason, just let us know. But otherwise, we're gonna shoot around during this hackathon. Okay, so let me talk a little bit about this research that I did. Sorry, let's see. So for most of 2025, I spent a lot of time testing the foundation models, frontier models, to see how well they understood physics. And I also was involved and am involved in a collaboration with DeepMind. That team has produced something called Co-Scientist, which is specifically a souped up version of their best model. No token limits. It's got an extra kind of internal structure that I'll describe in a little bit. And Co-Scientist is meant to be a collaborator that actual research scientists use, and ideally in the future it would have the status of, say, an expert human collaborator. So the work that I'm going to describe today is the outcome of that testing of generative AI and its utility for, in my case, theoretical physics. There are parallel results, very, very similar to what I'm about to tell you, in mathematics. So I won't go into that in detail, but for example, in an earlier podcast episode, I interviewed this gentleman who's a professor at UCLA, and his team produced, using this special architecture that I'm going to talk about, something we call Generator-Verifier pipeline. He was able to take off-the-shelf models and get them to perform at gold level competency on the most recent IMO, International Math Olympiad competition. Now, if you try to one-shot these problems from the IMO, typically you'll get it'll be able to do maybe 1 out of 6 problems. If you take the same model, but you embed it in this kind of pipeline that I'm going to describe, you can get it up to 5 out of 6 problems. And so one of the messages, I think, for people who are using AI in applications, one of the practical take-home messages is, if you are only one-shotting the models, you are not seeing peak level performance of the model. So it's possible you yourself have never actually experienced the full capability of the models if you've never tried to use this kind of generator-verifier pipeline. And jumping from 1 out of 6 to 5 out of 6 on the IMO is, I think, a reasonable example of that. And the research I'm going to talk about is related to that as well. Much of what I'm going to say is in this episode of Manifold that was released, I don't know, a few weeks ago. So if you're interested in what I say today and you want more, you can always listen to this episode. There's more in this episode about what I'm going to say. Now, as Jeremy said, this is possibly the first paper published in theoretical physics, so peer-reviewed, published in a journal, in which the main idea of the paper came de novo from a model, and in this case it was GPT-5. Now, interestingly, my co-scientist friends, I was spending all this time doing stuff with them, but co-scientists didn't actually generate anything that turned into a publishable research idea. It just happened that GPT-5 did. I'll explain the circumstances for how that happened. All this is a little bit disappointing to the co-scientist team, that co-scientists didn't generate the first idea that got published in a theoretical physics journal. But we continue to work on this. I'm sure we'll produce good things using co-scientists as well in the future. Now, Jeremy hinted at the idea that there was actually a negative reaction from the physics community. And I was too autistic or too, I think just generally a positive person who I have an open personality. So I just wasn't anticipating this even though I was aware of this, what happened to the Galactica, I just didn't even think this could happen in theoretical physics. Actually, I should say one more thing before I get into this. My plan with the co-scientist team, which we had talked about explicitly, was that if we got co-scientists to generate some good stuff and it turned into a paper, we would submit the paper to a good academic journal, but just under my name. And there are disclosures now that are required for almost every academic journal, at least disclosing that you used AI in the process of the research. And of course, in submitting this paper, I did make that disclosure. However, I did not say in the disclosure that the main idea of the paper was generated de novo by a model, because I did not want to bias the referee. So what the journal editor received was a submission from me as author, but with an acknowledgement that AI was used to some degree in the creation of the paper, which I think almost a pretty large fraction of the papers they're receiving have at least that kind of disclosure. So I think it's fair to say this received the standard review, the referee report and such, as any human-generated paper. So we wanted a fair comparison. We wanted a fair process that the paper would go through. And then what we had originally planned with the co-scientist team was we would then, after the paper was accepted for publication, we would then disclose that, oh, actually AI played a really significant role in this paper. So in my case, I wrote a companion article. There's a companion article which is currently also under review in a physics journal for a publication in a physics journal. That companion paper describes the process of how this research was accomplished. And much of my talk will basically be talking through what's in that companion paper. Okay, I won't go into the physics that much, if people are interested, I'm happy to talk about the actual physics, but that tends to be fairly esoteric for a general audience. Now, in this YouTube video, this is like an hour and 30-minute YouTube conversation, is an old friend of mine, Jonathan Oppenheim, who's a very well-known theoretician. He's at University College London. He works on quantum gravity and quantum foundations, quantum information theory. So he and I have very similar interests. We've known each other for, 20 plus years. And Jonathan and another professor, Nirmalya Kajuri, who's a professor at IIT in India, also an expert. I think Nirmalya is more of a string theorist, but also understands these topics pretty well. Both of them wrote very negative things on their blogs, on their Substack and blogs, about my paper when it came out. And then we got into conversations both by email, and then Nirmalya actually, to his credit, said, hey, let's just all get together on Zoom or whatever and just hash out what we think about the paper. And so if you're really interested in the reaction of the physics community, or if you've read negative stuff about this work, I suggest you go to the source. So that the only people that have really publicly said substantive negative things about the work are Nirmalya and Jonathan. So you can hear us discussing it, and I claim that any reasonable person listening to the discussion will conclude by the end that both Jonathan and Nirmalya agree there is non-trivial work in this paper, it should have been published, and AI is useful in physics. So don't don't believe random snippets of content that you see in social media. Just actually, you can see us talking to each other live on this video. Okay, so let me talk about the discovery process. So one of the things I was doing over the past year, I don't know if this is readable. In the companion paper, I have the exact prompts and the exact responses from the model at the sort of eureka moment and for other key components of the research. So during 2025, what I was doing is, I should say, sorry, little background. If you have been testing the models, the frontier models for their ability in physics or math, there was a tremendous improvement during 2025. So at the beginning of 2025, you could talk about models where you would ask it some simple thing like, I have 5 apples and I gave 3 away, how many apples do I have? And it would make mistakes on things like that. But the guys at the lab are working very hard on making the models good at physics and math. They are not only subjecting sort of every published physics and math paper on the archive and in a lot of leading journals to forward and backward next token prediction. They are sucking in huge amounts of they're paying $150 an hour for grad students to annotate physics problems and just provide even more bespoke training data. So there is a significant effort to improve the models in these particular areas of performance, and you could see it. So during 2025, there was a pretty strong gradient in improvement. And so in sort of the second half of 2025, I was spending a lot of time following this process. I would take an old paper that I had published, and I would upload the paper to the model, and then I would discuss the content of the paper with the model. And I wanted to understand how well the model understood the paper. For those of you who publish in academic journals, you know the most painful process in the world is dealing with your referee or referees, because they're anonymous and they can pretty much misunderstand, confabulate your paper with no consequences to them and make you jump through all kinds of hoops and cause you all kinds of emotional pain. And so what was interesting to me was to understand how well did the models understand these already published papers, say from 5 or 10 years ago, versus what I actually experienced with the actual human referees and editors, the people I presented the work to in seminars. And so I could sort of compare modal physicist versus model, and model was doing better than modal, I have to tell you, okay? So that doesn't mean they're necessarily capable of generating their own research, but on that particular metric, model was doing better than modal. And then the next step is that because when we write papers, we generally are, we've got a bunch of research, we've maybe got hundreds of pages of calculations in notebooks and things like this, and you have to select what do you want to be in the paper, what is the publishable core of the paper, what are the conjectures that you weren't quite able to resolve and can't be put in the paper, what are the calculations that were interesting but not interesting enough to put in the paper. So there's always some extra stuff which quite possibly has never appeared in the literature and therefore cannot be in the training data of the model, but you still might remember. So as I was going through my old papers, I could think of oh, we thought we could do X and we didn't quite push it all the way through, but I'm pretty sure this is right. But it's not in the paper, and it's I can check and see it's not been done by anybody else, right? So that gives a unique opportunity to test I'm sorry, there's feedback, but that gives us the opportunity to sort of test, can the model do something which is somewhat innovative and is clearly not just it recalling something, some compressed version of something that it read in some paper elsewhere. That's a big problem. That's the reason why these guys leap on the latest IMO or the latest Putnam, because those problems, hopefully, if the designers of the test are doing their job, have not, at least in that exact form, appeared anywhere else, right? So it's less likely that the models are just recalling the solution, they're actually solving the problem. So in the process of doing this, I was looking at a paper that I'd written, I think it was published in 2014 or 2015, and it was one that I knew the referees had had a lot of trouble understanding, although it was ultimately published. And so I was checking the model's understanding of it. It had a very good understanding of the paper. And then I started asking it about a particular direction of extension of what was in the paper. And so I gave it this prompt. Don't worry if you don't understand what that is. There's a lot of specialized terminology in there. But what's interesting about GPT-5 is GPT-5 has been RL'd to make sort of potentially helpful suggestions. So it responds to your prompt, but then something about its behavior, I think through RL, generally it will also make little suggestions about like, oh, would you like me to do X or would you like me to do Y? Now, in this case, it said, oh, if you want, I can sketch the Tomonaga-Schwinger version of this, evolution by space-like hypersurfaces, to show exactly why a hypersurface local generator that depends, okay, blah, 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 okay. But what's interesting about the suggestion is I was shocked by it. I said, wow, that's actually really interesting because that is not something I've ever seen anybody do. The model just suggested this out of the blue. And so I said, well, yeah, show me that. I want to see that, right? And it produced, you know how these models are, like it just immediately started cranking out stuff. It produced a page and a half. This is just part of it. So it produced a page and a half of absolutely correct and novel equations, okay, which form the core of the paper that eventually was published, okay? So is this a breakthrough like Einstein's theory of general relativity? Is it something like that? No. But is it a case where a model, at least combinatorially, understood two very distant areas of physics and combined them in a fruitful way? And in a way which, had this been a grad student who came to my office and said, oh, Professor Hsu, you asked me to read this old paper of yours and I had this idea and I worked these equations out, I would have been very, very pleased with that grad student. I would have been very, very pleased if a colleague or senior professor or postdoc had done this, right? So I think that's the level that you can get out of these models, okay? Yes?
Quick question.
Yeah.
Are these formulas like totally brand new or have you seen some sort of similar stuff in other papers? The reason I ask is because I wonder if it totally came up with the new formulas or did it already see something?
Yeah, so at the risk of getting into the gory details, so Tomonaga-Schwinger and Feynman shared the Nobel Prize for quantum electrodynamics. And that was really the first fully executed quantum field theory described in the literature. And Tomonaga and Schwinger came up with a covariant formulation of how quantum field, the state of a quantum field evolves from one space-like slice. So you see, to define time in a particular space-time, you define equal time slices and you ask how the quantum state of these fields evolves forward in time. Okay, so it's evolution from foliation to foliation. Okay, and there's a covariance condition that Tomonaga and Schwinger, I think it was actually Schwinger, wrote down that that formulation has to satisfy for internal consistency for relativistic covariance. Now, what the model did was I was interested in the question of if we modify quantum mechanics to add some nonlinearities to the Schrodinger evolution of the theory, what special constraints on that nonlinear modification are required for you to do quantum field theory, as opposed to just describe like a spin or an electron or something. But in the case of quantum fields, you're describing an infinite number of degrees of freedom simultaneously, because the field itself has an infinite number of modes that can be excited. So what it did was basically take the nonlinear Schrodinger equation for quantum fields in the Tomonaga-Schwinger formalism and then apply these conditions. And then it derived, so this n hat thing, this curly n hat thing is the new term that you've added, and it basically derived a bunch of conditions that n has to satisfy. Again, it's not super deep. It's not like someone saying, oh, I think space and time could be curved, and I think that curvature is driven by the energy momentum tensor, or like it's not like that, but it is non-trivial. So, yeah. Question.
Yeah, if it's too detailed, I understand, but is in the training data and is likely in the RL data, where this question of attaching constraints and evaluating which are and are not necessary, as well as just sort of other high-level patterns of research
So if
are in the training data.
you know, I could apply, yeah, I could apply theorist psychology to anything like one of my colleagues says to me, or to a model. So I can say, like, where did they come up with that, right? So here, I don't think the leap is that powerful in the sense that what's going on here is that you have a certain rule, dynamics for evolving the quantum state, and now we've modified it because we're contemplating allowing these nonlinearities, right? And it knew that for quantum field theory, there are these important constraints that need to be satisfied. So it said, like, oh, well, let's see if this thing satisfies those constraints. And then it worked through, you know, some somewhat fancy math to get these commutation relations, right? So the base logic is nothing like, again, it's not some huge leap like that Einstein made, but it is non-trivial. And I think it comes from the fact that the models have read everything.
So what part
So,
of it is non-trivial? Is it just be asking the question? Is it the working through of the constraints?
well, I think,
What part is non-trivial?
yeah, so what's non-trivial is like the average, like if some grad student came to me with this, I would say like, wow, how come you're so familiar with the Tomonaga-Schwinger formulation? Because the Feynman formulation, became the predominant one. And very few people are actually familiar with what Tomonaga and Schwinger did, even though in some ways it's actually better than what Feynman did. But very few people are familiar with it. But the models are familiar with everything. So a combinatorial thing where there's there's a set of techniques here, which, these come from condensed statistical physics, and most particle physicists don't learn these. But most statistical physicists don't know about this particular interesting problem in particle physics. And just combinatorially having just way broader knowledge than us, the model can be like, oh, okay, let me just glue these together. And so I would put it more in that category. Yeah.
So David Holst was here saying these models are superhuman at blending.
They're superhuman, yeah, and they, right.
In statistical physics.
Yeah. So they've read everything. They just have much better knowledge of everything than us. Now, just leaping ahead a little bit to ask, what is the cost-benefit analysis right now for working heavily with the models? Interestingly, in that conversation I had with Jonathan Oppenheim and Nirmalya, Nirmalya is younger than we are, and he's, I think, an assistant professor, and so he's more in touch with the younger physicists. And he surprised both Jonathan and myself when he said, like, I think 70% of younger theoreticians, under 35, are using the models heavily in their work. Okay. Now, what is the cost-benefit analysis of using the models, right? So trivial errors are becoming rarer and rarer. So in other words, if there's some algebra, like I might have made a bunch of errors in, like if my student had come to me and just had the first part and said, hey, can we work out this stuff? I might have made a bunch of like algebraic errors, you know, or missed some term here or something. It does that less and less. So it's becoming fairly rare for it not to be good at algebra and just simple manipulations, calculus, linear algebra, stuff like that. It can still hallucinate. It can still pretend that a plausible statement, blah, 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 totally wrong, right? But it's becoming less and less common. The main pitfall, I would say, in the models is that it will come to you trying to be helpful. And it will say, oh, you know, so-and-so derived this set of theorems, which actually can tighten the bound that you're looking for. And you're not familiar with that whole line of work, right? And then I have to then, and this actually happened in this research with a different aspect of this research, you have to spend 10 or maybe 100 hours figuring out finally that, no, this is a wild goose chase. That's not what those theorems say. Plausibly, maybe you could hallucinate that that's what those theorems say, but they don't actually say that, and they're not useful for what the model. So that kind of wild goose chase phenomenon is I think the largest cost in dealing with the models. If you're just using models like Mathematica, where you're like, I have a well-posed thing for you to do, like just simplify this algebra for me, it's getting very reliable. And at that point, it just can become like a Mathematica that you can use natural language in talking to. But letting it actually connect some distant areas of techniques for you is dangerous because it could often be wrong, and often it takes you a long time to figure out that it's wrong. So coming back to this generator-verifier architecture, which in this earlier manifold episode, I interviewed the UCLA professor who had used it profitably for IMO problems. In the case of IMO problems, for those of you who don't know, you're not just solving the problem, you're actually writing a proof. So to get full credit on one of these problems, you're asked to prove a particular thing. So you have to actually generate a rigorous proof. What the generator-verifier architecture does is you create different instances either of the same model, like say you're always using Gemini or you're always using GPT-5, or you could even have different models in this pipeline. And some of the instances are prompted to be sort of generative, so they're being asked to like try to prove this, or come up with useful calculations related to this, or come up with partial steps, right? So that's the generate part. But then you immediately show that output to another instance of the model or another instance of another model, and you ask it to critique it, find bugs in this proof, find errors in these equations, find mistakes in logic, okay? And if you chain that together, so then you take the output of that and then you let another generative kind of modifying AI instance see it, and you just push it through. That tends to suppress these wild goose chase errors. Because it could be the case that one of the verifier instances actually notices, like, no, that theorem doesn't say what you think it says, and actually it's not relevant here. And then the other model says, oh yeah, I guess so, let's just drop that. And so if you don't look in at that, you pass things through a pipeline, you only look at the output, the wild goose chase things, the red herrings tend to be suppressed, or the output has like an argument in it where you can see there was not a convergence between these different instances in agreement that that wild goose chase direction is actually useful, right? So either way, at the end, you get something which is less likely to eat up a chunk of your time fruitlessly, right? And so for me personally, I think that generator-verifier chaining of the models eliminates one of the worst aspects of the cost-benefit trade-off of using the models.
Do you think it would be a worthy project to fine-tune a model with this training data generation process in mind so that it internalizes the auto-critique? And have OpenAI already taken this as feedback and thought, well, actually, let's train to do this automatically?
So in their case, they have a GitHub repository for their paper. So you can go look at it, and they have code which basically, if your goal is to generate a proof of an IMO-like problem, you can just run their stuff, and it runs with any of the frontier models. But in the case of Co-Scientist, which is the DeepMind project that I'm involved in, they also have built an internal pipeline where multiple instances of the model look at things. And you can even tune up and down like rigor versus creativity that you want in different stages of this. I think the issue is I would like to see various versions of this made available to the general public in an easy to use, general public meaning like researchers, okay, whether engineering or physics or biology, whatever, but in such a way that people can work with it and we can refine exactly how these things should be built to make them maximally useful for a particular field of research. One of the things I should mention though is these things eat incredible amounts of tokens because it's sort of like at least one order of magnitude more tokens than from one-shotting it because you're just like pushing it through 10 inference steps, right? So that can be a problem, right? Because obviously, even if you just want the like, what is it, the like deep research, what is the GPT, the most?
It's deep research.
It's called deep research, right? So even that, like they might be metering you on that and like, so general people don't necessarily have access to that, and even some researchers wouldn't. But what I'm trying to talk to the labs about doing is like selecting, like go on archive and pick some active people that you think are worth like giving free access to this kind of thing, even though it uses a lot of tokens. But it'll generate like training data that'll make the models much better at science. And I think that will be done eventually. Yeah.
I think maybe the question, if I'm understanding correctly, is more kind of like, do you need a plan to do this, or could like the foundation models basically do training, just like reasoning models?
Yeah.
So they basically do this generating verifier.
Yes. So already, you can ask questions of like, well, how are these chains of thought generated, and to what extent is the model calling another instance of itself in that chain of thought or not? And I think the labs are aware of this. Now, I think the most interesting move in that direction, which some people who are real connoisseurs or conoscenti will know about, is DeepSeek briefly released a model, 3.2 Special. How many people know about Special? Okay, so 3.2 is a very strong model, but they briefly released, I think they only gave access to Special to the general public until December 15th, and then they killed it. At least that's what they said. Maybe they haven't taken it down. But so Special has a souped up reasoning capability, and Special out of the box without these kinds of optimizations also scored 5 out of 6 on IMO. So that's the first model that I think incorporates a lot of this stuff just inside without building this extra kind of crappy scaffolding or something, right? But they didn't leave it up because it uses a shit ton of tokens, right? So, but it shows you what's possible, right? So one of the things I say to the critics, I think I said this already once, but when some other physicist tells me, yeah, I use this thing, but it just obviously gives me crap. And I'm like, well, are you actually getting the best performance that models are capable of? Or are you just one-shotting stuff and then you're complaining because the one-shot stuff isn't that great? So, yeah. How much time? Oh, yeah, go ahead.
Just a quick question. When you say co-scientist here, is it going to be subject matter for each, or is it going to be multidisciplinary?
This is a great question. So the co-scientist team at first, they were just inviting some kind of lucky researchers to come in and like help them tune this thing and experiment with this thing. And their first emphasis was actually on biology and maybe some stuff like kind of chemistry, but stuff where I could see when they let me in, the models were tuned in such a way that they were very creative, but would often say things that are wrong. And I think they were just assuming like, oh, well, someone's going to run this through a mouse model or some cell line or whatever. I just want the model to be creative. It can say 10 creative things and you just put your army of NIH-funded grad students on one of them on each. And then like, if one of them turns out to be good, then fine, no problem, right? So it's like, that's not what theoretical physicists do. Like, I don't want to hear like 10 like bullshit, like wild goose chase ideas from this model, right? So right away I was on these guys. I was like, dude, your thing is tuned for biologists, it's not tuned for physicists or engineers. And so yes, there are going to be different flavors of this over time, and there'll probably be some like setting, like, oh, I'm working in this field, and then, oh, we found that these settings are the best for people working in this field. Yeah.
You have time to give us your best ideas, so whatever you think is worthy.
Let's see. Well, I think I more or less covered the status of this paper. I think this paper, is just going to be a footnote in history. The paper itself is not that deep. This question of whether quantum mechanics is in fact not precisely linear is actually one of the deepest and least addressed problems in physics. If you've had physics, you'll just remember that you were told that it's linear. And that everything can be expressible in terms of the evolution of a state vector in a infinite dimensional vector space. Maybe that's not true, actually, and it has very deep consequences if it's not true.
So the linearity is an approximation, much like mechanics.
Okay, so if
there are conditions under which it might be deeply nonlinear.
If you're coming from any other area of science or any other area of physics, like say you're studying fluid mechanics or something, if you write down the Navier-Stokes equation, someone might say, is that equation exact? Or is there like some other term here? Of course you'd say, well, of course there's some other term here. This is an idealization. But in fundamental physics, we're actually saying this is the way the universe works. And so it's very important for you to decide, is the Schrodinger equation an approximation to some other equation? Or is it actually the way that the quantum state of our universe evolves, and is it strictly linear? That's a very, very deep question, and very few physicists spend time thinking about it.
What do you get when you ask AIs to answer?
When you ask AIs about difficult, really frontierish questions, generally they will give you answers which are really from the training data. And so they will reflect a kind of maybe citation weighted or like attention by the physics community weighted summary of what the consensus is. And so that's another sense in which I can see the models to someone like me, do not pass the actual Turing test. So people claim like, oh, Turing test, we zoomed past the Turing test, and everyone forgot about it. The correct statement is actually, if you are a frontier research scientist, you know of cases where the community is wrong about something, right? Otherwise, you're not worth shit, okay? If you don't actually have some alpha over the community on something, like something that you really know and the community is like slightly wrong about, then you should quit. But if you do know some stuff where the community is wrong, the models are going to reflect what the community thinks. And if you start having a discussion with the model, we were discussing this at dinner last night, actually, you can briefly push it in the direction of what's correct, but then as you continue talking to it, you'll see it it's kind of like this Golden Gate Bridge thing. Like it kind of like will start to revert back to the consensus that was in its training data. And that's not how your grad student behaves. That's not how your collaborator behaves. If I explain why the community is wrong, like this set of arguments that's normally accepted as okay in the literature, this is why it's actually wrong. Generally, your well-trained human colleague will update on that, and then they won't like sort of like drift back in the other direction. Maybe they will, but after one or two things, they'll stop. One or two corrections, they won't drift back. But the models will always drift back. So to me, that is really important, because at the frontier of human knowledge, you can see they're not actually able to do continuous learning or real-time learning, et cetera, et cetera. The question in the back.
Yeah, have you had any rumors what's happening in, say, the Genesis project or any secret project in the Chinese Academy of Sciences?
Well, to be honest, I think Special is the most interesting thing, and that wasn't secret. They were just like, here, you can use Special if you want for a while.
So they don't have a secret journal where they're doing experiments with the guy data?
Say it again.
They don't have a secret journal published in the Chinese Academy of Sciences about the experiments that are not public?
Oh, well, on both sides there are classified results. So there are things like, what is the way that we, push the plasma that's generated by the cone of a hypersonic missile so it doesn't interfere with the satellite communication? Like, there's all kinds of like classified stuff that's not in the general literature that both sides have. One thing, just on that point, I have a friend who's a very prominent. He's a PhD in CS from the US, but he's back in China. He's a very prominent venture investor. And a few years ago, he said, the depth of knowledge now in China is greater than in the US.
Because they also have Chinese.
Because they all read English, so they all read the archive. But then there's the equivalent of Stack Overflow, all in Mandarin, where they're very deep, like there's some particular paper of focus that they think is really important, and then there'll be very, very deep discussions of that paper, but it's all in Mandarin. And so he says, he was saying to me, he can see like a kind of deeper knowledge base emerging in the sinosphere because of this accident of history that they were all forced to learn English, but then they also have their own language. And US researchers can't read that. But the models can actually read it, so I don't know, this may be going away.
Thinking about this, has anyone tried to aggregate knowledge both across English and Chinese literature?
Yeah.
Combine them, which currently people don't have visibility into?
So I suspect that, again, for this reason, the people who work at the Chinese labs understand English and they read the English language archive, but they have their own stuff. So I actually think they're closer to being a superset of all the knowledge than the guys here. Although, if you go into Mountain View, what is the pavilion called, where they do where the AI guys are, you hear a lot of Mandarin. So the difference may not be that great. The other thing what was the other thing I want to say?
Google Pucks?
Sorry?
Google Pucks?
Google?
Charlie's?
Charleston East.
Charleston East.
Yes, that's the CE building for the big fund there.
I found, it's called the Gradient Pavilion, right?
The gradient canopy.
Gradient Canopy, yeah. So in that building, I hear a lot of Mandarin. Okay, so maybe this whole thing is like, it's pretty symmetric, actually. Yes?
So, great talk, by the way. There's this arc of your talk, which is sort of, in the Valley, we call it systems engineering. And I think in physics, you'd say how the theoretical side interacts with the experimental side. And so you're kind of elucidating that and allow you some more theory is, what would be your ideal, you kind of touched upon it, your ideal, what would you want from the computer scientists? What would you want from the experimentalists? How do you feel the system engineer? So this is, for for instance, one offshoot is that peer review perhaps needs a improvement, needs a re-architecture, right? To catch some of this, maybe make it softer in some respects and harder in some respects, right? Yeah, so what's your...
Well, one slight comment on the nature of this work that I'm talking about. This is purely theoretical work, so we're not consulting the real physicists, the experimentalists. Okay, so this is something that some people who are maybe not that familiar with how physics works find surprising. So there is quite a divide between, maybe theorists are something like 10 to 25% of the population, and the rest of the field is experimentalists. People who actually build stuff in the lab and collect data, and those are the real people. And you could even argue like theorists are parasitical on them. But there's a lot. Like what I'm showing you is like a little bit of a microcosm of like, oh, theorists are arguing about the properties of this proposed alternative model of physics. And the models can help with that. So that's more or less all I've demonstrated. I haven't said anything about how it would help an experimentalist design something to test this. I haven't talked about, so there's much more than what I'm talking about today. So I don't know if that addresses your point.
No,
yeah.
I would give you, I like sort of the directions you've gone, and so I want like, what's the next post? What is your intuition?
Well, I think, okay, so big picture, I think that the gradient in capability of the models in 2025 in math and physics that I saw was tremendous. Okay. Now that doesn't make me a doomer or think that AGI is right around the corner because, for example, they can't even pass the Turing test. Okay, but they are getting really good at certain things, right? So it's more a question. It's more a statement of like narrow AI can always beat humans if you really know what you want to do, have the model do. But I think that we are not near the ceiling of the ability of these models to do math and physics. And so like I can easily imagine a time where it's much more valuable to me to like wake up and just start talking to the model about my physics research than to go in and get a cup of coffee with my colleague down the hall. It really, I think we're very close to that. We're within a few years of that, I think. And I think that's surprising to a lot of people. In math, it's even more pronounced because the objective function and the cleanness of evaluation of what the model did is much better than in physics. And so like you'll see, if you read Terry Tao's blog posts, you'll see him like basically like, oh yeah, this Erdős problem got solved and the model basically cranked this thing out and I checked it and it's right. And wow, if I had a grad student who could do that, I would be pretty happy, right? So I think we're going to see a pretty big acceleration in the role of these models, at least in these kind of more theoretical mathematical sciences.
So would it be like you're having a conversation with Einstein, basically?
Maybe not Einstein, but because Einstein was special. I mean, he had some insights that maybe the models wouldn't have, but definitely maybe model maybe beats modal. Model beats modal physicist, maybe. So you've been waiting for a while. Yeah, so I want to say again, like what attracts the attention of people who are outside of physics about physics is these like grand unified theories and deep ideas and stuff like that. But what really determines the pace of progress in physics is our ability to do experiments. Like, so right now we're in a situation where there are lots of really interesting potential theories of how the universe works, but we don't have the experimental data to differentiate between them. And that data is very expensive to get and technically challenging to get. So the models themselves actually are good at the following type of thing. If I say, suppose I make this modification of the standard model of particle physics, would this already have been seen above background in collisions at the Large Hadron Collider? The models are actually pretty good at making estimates and saying, well, the background is this, and you probably would have seen this signal. So they're good at that. What I don't know whether they're good at, because I'm not an experimentalist, is how useful to an experimentalist who's trying to like, oh, I think if I change the shape of my door, I can keep the temperature low for longer, and I can test the quantum coherence of my qubit for, and what, how useful are the models to them for those kind of very practical experimental physics laboratory type things? I don't know the answer, but I think it's possible they could be quite useful. A lot of questions. Okay, yeah.
Can you give like an approximation to that question? How useful they would be to experimentalists from the biological side? In a sense, like you said, that when you started working with the co-pilot model, that like people were working with like in biological sciences.
Yeah.
Biological sciences are heavily experimental. So like any insights from that side?
I think the claim I'm hearing, I'm only hearing this secondhand because I hear it from the co-scientist AI researcher at DeepMind, but I'm not directly talking to their client, their customer, who's the molecular biologist, right? But I think they say that their customers are happy in the sense that you're a big. This is how modern biological medical science works. You're this big PI, you have this big name, you're at UCSF or Harvard, and you write these horrible grant proposals that are huge like this, and you're funding like a bunch of grad students and postdocs who literally do all the work. And in fact, the ideation for your grant proposal might be from your team, okay? So for those guys, if the model comes in and the model reads their grant proposal and it says, oh, here's a set of things you didn't think of, you should try this. And those guys then say like, yeah, this is just as promising as this shit we wrote for NIH. This is actually more promising than what we wrote. So maybe we're gonna do that. So they are happy. Now they could be wrong, but they are happy, I think, with what the models are doing for them. The models can do ideation at a level that their postdocs and team can do. But of course, if 9 out of 10 of those ideas are wrong, it's still okay, as long as that one is correct. Physicists, we don't want to put up with that. We don't want to have like, because our stuff is a little more tightly constrained. Yeah.
What do you think about, there's at least one platform I know that's doing peer review, AI-based. What do you think the social impact will be?
Well, I think actually model beats modal. So I actually think like if a journal, of course there'd be a huge prestige hit and people would be very angry and there'd be a lot of feels. But if the model said, oh, we're going to first pass referee step is, well, I'm hearing music. First pass is an AI, and then maybe we bring humans in and save the human attention. I think it would improve the level of review by journals. Yeah, and also, I don't know, is that music coming from me or? Okay. Yeah, this is my cue that I'm done. I'm out of time.
Steve Hsu.